Continuing on in our chapter 4, our second chapter 4, unit 4, we're going to talk about data distribution. Some of this might be a review from middle school. Hopefully it will be just like the last section, and maybe get into some new stuff as well. Dot plots. They are used with simple data sets of about 20 points. If you get more than 20 points, dot plots might not be the best bet. It gets a little bit too messy. Then you would want to use histograms. Histograms are used when there is a larger amount of data. Generally 20 is a good amount of data points to cut it off if you have that many. Pause the video, write down those definitions. They're not really definitions, just some explanations there. All right, so first we're going to look at these dot plots. It's a little blurry here, but you're looking at a dot plot with a number of siblings. So how many siblings does a person have? So we can read this, but we can see that for 0 siblings, there are 4 dots. That means we had, in our sample, 4 people that had 0 siblings. You can do the same thing with your 1s, your 2 siblings, 3 siblings, and then you can see that there was 1 person who had 4 siblings. Okay, 3 people had 3, 6 people had 2 siblings, okay? So what we can do is we could also rewrite this data 0, 0, 0, 0, 4 times. And then you could write out your 1s as many times as you have dots here. Same thing with your 2s, your 3s, and your 4s. Obviously, this would be a ton of numbers, and it wouldn't be that great to look at, a little unfriendly to look at. So it's nice that we can do it in this manner with these dot plots. Okay, so you guys know how to find mean, you know how to find median. Go ahead and do that now. Pause the video, find the mean and the median. Okay, so for the mean, we know we need to add up all of our data and then divide by however many pieces of data there were. So when I added these all up, I got 33. Kind of a quick way to do that, I got 1 4 here, 3 3s here, but that's really just 3 times 3, so that'd be a 9. 1, 2, 3, 4, 5, 6 2s, which is a 12. 1, 2, 3, 4, 5, 6, 7, 8 1s, so that would be 8. And 0 is still going to be 0. So 8 plus 12 is 20, plus 9 is 29, plus 4 is 33. So kind of a quick way to do it versus 2 plus 2 plus 2 plus 2, just a little multiplication. Adding up all the data points, we had 1 here, plus 3 is 4, plus 6 is 10, plus 8 is 18, plus the 4 more gives you 22. So the sum was 33, the number of data pieces you have are 22, divide that out and you get 1.5. So the mean number of siblings is 1.5. The median, there's 22 pieces of data. We would want to put those in order and find the one in the middle. Well, if you've got an even number, you don't have one in the middle. If we've got 22 total pieces, we would have 11 on one side and 11 on the other. The middle piece, there isn't one because it's the even number. So then you have to find the 2 middle ones and take the average. So essentially you want the 11th and the 12th, whatever is in the 11th and the 12th spot. So here was 4, and there's 8 here, which means your 11th and your 12th spots would be right there. There's 11, there's 12. Well, both of those represent 1s. So 1 plus 1 is 2, and 2 divided by 2 is 1. So the median number of siblings is 1. Okay? All you're doing is really finding the mean of those two numbers. Okay, hopefully that's what you got as well. If not, you definitely want to correct it. Okay, let's talk about histograms. So histograms look like these. Remember seeing these before? Whoops. We want to talk about how they can be distributed, what the distributions might look like. The first graph here is a symmetric graph. Okay, you guys know what symmetry is. It's the same on one side as it is on the other. You're very symmetrical in this distribution. This is also called sometimes a bell curve. You can kind of see that it looks like a bell. You could ring it, a little ringer would be down here. This one over here is called bimodal. Okay, so you have um, kind of two different main data points like we did over here. So what could be an example of these different types of distribution? An example of your bimodal might be the number of tires people have at their houses. Generally, you know, a car's got 4 tires. Well, maybe you have one car, and so you would have an average general distribution where you've got 4 a whole lot of times in your sample. Or 8, maybe you have 2 cars. Okay, but generally people aren't going to have 6 tires or 3 tires because you're driving a car, the car's got 4 tires, you're going to have some multiple of 4. All right, then we have ones that look like this, and we call this skewed data. Skewed meaning it's off to one side more than the other. What I think gets confusing is which way you call it skewed. This particular example, this one's skewed left. And oftentimes students want to say it's skewed right because the hump is in the right, but the skewing is happening to the left because most of your data is here, but then it gets skewed on the left side. Sometimes I kind of just interpret that as where is it messed up at? Well, it's messed up on the left. You've got all these small data points to the left. And the bulk of your information is to the right. So the skewing is on the left. Okay, so then you should probably guess what the other one is. It is, of course, skewed to the right. The bulk of your data is happening on the left side, and then you are skewing, getting these extra pieces off to the right. Example of skewed left data, could be GPA. Okay, you've got a lot of people with maybe like 3.2s, 3.3s, couple people with these high 4.0s, and then you kind of go down from there. So maybe some 3-point or some high 2-point things, and then just a couple with the very low GPA. Skewed right data might be your average household income. Okay, so you've got a lot of people in this general region right there. And then you got a few people, very small amount of people who are super, super rich. Okay, and you have a very small amount of people who are very, very poor. Okay. Another thing with the bimodal, remember the word mode. Mode means what's occurring the most. So it would make sense that in this distribution, you would have 2 modes, 2 main numbers that you are hitting there. So bi meaning 2 and modal meaning mode. Okay, the mean on the move. Compare the mean versus the median of a skewed data set. So we've got 3 different versions of this. This one, of course, is your symmetrical one. This one is skewed, and so is this one. Now remember which is which. So if you look back here, the small area is the direction we say that it's skewed. Okay, so skewed to the left means your hump is actually to the right. So this one would be skewed right, and this one would be skewed left. If you're symmetric, your mean is equal to your median. Hold on, I've got something I wanted to click here. Okay, so your mean and your median would be equal if you are symmetrical. Your median is right in the middle, and your average is right in the middle. It's the balance of all of your data. When you're skewed right, your median is the data point in the middle, but because you're skewed and you have all these extra data points going this way, it's going to pull your mean down towards it. Okay, so you're definitely not going to be equal. Your median is going to be less than your mean, or I like to think of it as your mean is going to be greater than your median because the mean is pulling it up. If you're skewed to the left, here's your middle of your data right here, your median, but these extra points that are down here are going to pull your mean down. So your mean is less than your median. For skewed data, it's actually better to use the median. okay? Because those extra data points that are happening where it's skewed, they're going to change your mean. They're going to pull your mean towards that data, whereas that won't happen with the median, okay? So it's better to use the median rather than the mean when you're dealing with skewed data. It gives you a better center of the data, and that's what we're really finding here, is what's in the middle of the data, what's the average of the center. All of those words can be used. Okay. Tell whether the following distributions are more likely to be skewed left, symmetrical, or skewed right. So let's talk about the age of death in a city. Okay, well, generally you'll find that people don't die when they're young. Of course, you have instances where it does happen, but in general, we're talking when people are dying, they're generally older. They're going to be more elderly, and that's a good thing, right? So go ahead and draw a picture of what that distribution will look like, what that histogram will look like. Okay, so I have something like this. You should have something roughly like that. Maybe yours is a little more like this. That's okay. But we would say that this is skewed left. Okay, we have some extra little points over here, but the bulk of our information is over here on the right. Okay, foot size of a 30-year-old woman, so foot size of 30-year-old women. Think about foot size if they're all the same age. So we're not talking about like babies, kids, adults. If we're talking about the same age range and the same gender, I'd say that would probably be symmetric. You're going to have most people having kind of like an average size. Maybe that's, I don't know, 8. But then you've got some people who have these smaller feet, 5, 6, whatever. And then you've got some women who have some larger feet, getting into 9s, 10s, 11s, whatever. But the bulk of your information is going to be right in the middle and just a few going on each side. Okay, estimate the mean and median from the graph. So here we have a dot plot. Keep in mind what you've got going on. Your median is cutting your data in half, and your mean is your balancing point. So we could find these exactly, but they've said estimate, so we don't need to find an exact number. We do want to cut the data in half. So you want just as much on the left side as you do on the right. Okay? So if we cut our data in half, if we want just as much on one side as the other, I think your median is going to be 1. If you want to find that exactly, count up your data points and cut it in half, find your middle point. But your median on this one, I can eyeball that and I can see that it's going to be 1. Now when you're thinking mean, think not cutting in half anymore, think about your balancing point. Think about a teeter-totter. Okay, if you have 2 people on a teeter-totter, I know you like my drawing, you're not just necessarily going to cut it in half, because what happens if one person is much heavier than the other person? They're not going to be able to move that teeter-totter up and down. So what you do is you find the balancing point. Okay, you would have to take your take and move it so that you've got a better balance, and that's what the mean is doing. So your heavy points or your very small points, they're going to move your mean around a little bit. In this case, your mean, if you needed to balance it, you can even think of this as a teeter-totter. Where would you need to put your finger? If you had this line and you were trying to balance it on your finger, like this was an actual physical thing with maybe blocks like this, and you were trying to balance it, where would you put your finger? Certainly you wouldn't put it like over here, because this side would be so much heavier, it would go down very quickly. So where would you put it? Right in the middle of all of your just 0 to 7? No, because again, this side's heavier. If you put it where your median is, you've got too much then on this side. Okay, so we could say here, I think it needs to be over maybe just like around here, maybe like 1.5. And again, this is an estimate. It's not an exact answer. You could actually do the exact, but that's not what the question's asking us to do. Quick check of this. Which way is this data skewed? I would say it is skewed to the right. You can draw this shape, right? It's skewed to the right. And what we said on the last page was when data is skewed to the right, the mean has to be greater than the median. So that's how I'll check your work. If it's skewed data, you need to make sure your mean, if it's skewed to the right, your mean has to be greater than your median. Take a look at this one. We're not skewed to the right here, we're skewed to the left. When you're skewed to the left, your mean is less than your median. So that's how I'm going to check them. It's okay if they're not exact, but that principle still needs to be there. Okay, so pause the video and you guys try and estimate the mean and the median from this graph. Okay, I came up with the median to be about 17, splitting the data in half. And be careful, I don't mean I'm splitting my numbers from 0 to 25 in half. Obviously, that would be 12 and a half. I'm splitting my data points in half. Okay, and I'm thinking that should be somewhere in this region, and that was going from 15 to 20, so I'm saying about 17. The mean, though, the average, these numbers are going to pull that average down, so I made that about 15. Again, you're skewed to the left. When you're skewed to the left, your mean has to be less than your median. Okay, and then stem plots. Stem plots, sometimes called stem and leaf plots. The stem repeats its value, and each leaf then represents a data point. Okay, so I really like using these. They're a quick way to write information. Let me go this way. So you have two examples here. This is the stem plot of ages in a church choir, and they have to give you a key so that you understand how to read it. So 3 and then your bar 1 represents 31 years old. So this data here would be 15, another 15 because you're repeating the stem and then you just put the leaf on it, and then repeat again. The 1 with the 6 makes it 16. So this would be 20, 23, 23, 24, 26, 26, 28, 31, 34, 36, 43, and 43 again. This example over here, the length of worms that were caught in centimeters. Now check this one out. The 6 and the 2, it's not 62, it represents 6.2 centimeters. So this is 3.0, 4.5. Now there's no leaf on this one, which means you have no values that are 5 point anything. You do have a 6.2, 7.1, 7.7, etc. You can read those all through. Okay, you can also think of these almost as a dot plot or a histogram. You just have to look at them sideways. So you need to kind of rotate this way so that this is your baseline and then these are going up. And if you do that, this one, you might think it's slightly skewed, but it's pretty symmetrical. Okay, so I would say this one is a symmetric distribution, whereas this one is very obviously skewed. And again, you're rotating it. Let me actually do that. Oops, I can't do it on that, but I can do it on my line. So if I take this and rotate it so that my numbers here would be down here, then you can see that this is skewed which way? It is skewed left. Okay? So those are stem and leaf plots. Lastly, an outlier, which we talked about in the last section, but just to reinforce that, an outlier is a number that is really far away from the rest of the data set. So if you look at this, the length of the worms caught, 3.0, 4.5, 6.2, 7.1, most of your data is right here, right? Okay, roughly. These two numbers, 3.0 and 4.5, those would be outliers. In this one, you've got pretty much, again, symmetric data. You don't really have anything crazy. But say I added to this data maybe 92. 92 would be an outlier. That's very far away from the rest of the data. Lastly, explain the effect of an outlier. Explain the effect an outlier would have on the following. On a mean, if you have a crazy number, think about a neighborhood where everybody is a teacher, everybody's making the same salary, and then a millionaire moves in. Okay, well, that's obviously going to greatly increase your mean because you're taking an average maybe $40,000-$50,000 salary and then putting $1 million or $2 million or whatever million in there. That's going to change the mean. It's going to pull it towards the value of the outlier. Same thing if you had an outlier that was very small, it would change it and make your mean less instead of greater. Median, your outlier will not change the median because all you're doing is splitting up your numbers. So if you have the numbers 1, 2, and 3, your median is 2, right? That doesn't change. That's what it is. But say I have 1, 2, and 500. That median is still going to be 2. It's not affected by this outlier of 500. Whereas you could see on the mean, that's definitely going to change your mean. Last one, standard deviation. An outlier will increase the standard deviation because standard deviation is measuring how varied your numbers are. So if you're looking at a basic sample of 1, 2, and 3 without an outlier, your standard deviation is not going to be much. Your numbers aren't varying. But if you make it 1, 2, and 500, you have a big variance in your numbers, so your standard deviation will increase. Okay, finish your packet.